Welcome back to che531. This is part 4 of linear programming. In the last video I was talking about an example where the solution to a linear programming actually could be so I talk about the problem that there was no solution to a linear programming problem. And pictorially, I was talking about how or why we do not have a solution. So just quickly recap, we had an optimization problem to maximize this function subject to two constraints with the non-negativity constraints as well. We drew these inequalities as well as the objective function. So this is the objective function. We just drew it for a given z value. Remember, we just set this to z, and then for different values of z, you can have different lines, but for a generic z, you're going to have a line with this slope as you change z. So for plus z, this line is going to have a plus intercept, and for minus z or negative z, then this red line is going to have negative intercept with the x2 axis, and the slope of this line is minus 2. Because if you set this to z, right? So if I want to be more clear on this, then I rewrite this objective function as follows. So you can say z is equal to 2x1 minus x2. Okay, I can move my plus x2. I can move my x2 to the left and everything to the right. So then becomes x2 is equal to minus 2x1 plus z. Okay, so let me move it to this side. Now, imagine this is y and this is x. So y is equal to minus 2x plus z. So this is a line exactly like this with a slope of minus 2. An intercept of z. So this z is going to be the intercept. And as you see, if I change my z up and down, then this line goes up and down. The goal is to maximize z. Okay, now imagine z is the intercept, and my feasibility region is the region I hatched here. The question is, where is the corner at which I get the highest intercept for this line, right? So I put this line on this point, and then move it to this point, and that's it. I do not have any other corners because this feasibility region is unbounded. So for this, if I move this line on this point, then I get a line like this. Let me make it red so you could easily see. Okay, so this is the line I just moved. Oops, sorry. I have to keep the slope. So this is exactly parallel to this. Let's say this is parallel, like that. Okay. Now I move it to the same slope. I move it and put it on this point. So for this point, the z is going to be 0 because that's the intercept. So that means if I use this point for x1 and x2, my z is going to be 0. Then I put on this corner. So my z is going to be a bit more, maybe about 1. I put on this point. My z is going to be this much. Okay, you see that I'm still maximizing my z. Now it looks like there are more points, like if I move along this line or along this line, I can get a higher and higher intercept. You see my intercept is increasing. And again, intercept is the z, which is the value I want to maximize. So this is unbounded. I can go as much as I can to the right and my intercept goes up. So there's no solution to this problem. That means the maximum of this function is infinity. Okay, so I hope this is clear that sometimes we run into problems that there's no maximum. Actually, the maximum is unbounded. All right, so let me move this one back to this point. All right, so now the last thing I want to talk about is, before actually I jump into talking about MATLAB functions or built-in MATLAB functions, I'd like to give you one more example from this other textbook So I post this on Blackboard. This is another textbook on simplex method. I really recommend this book. Look at that. There are a couple of examples with a really clear explanation of how simplex method works. So for the sake of time, I just quickly go over maybe one of the examples of this book. Imagine we have an objective function like that. Z is equal to 4x1 plus x2. All right, and we want to maximize z subject to 3 constraints. Okay, so we know that we convert all the inequalities to equalities using basic variables or slack variables. So we're going to add s1 to the first equation, we convert it to equality. We add x2 to the second equation, convert it to equality. And then we add s3 to the third equation and convert to equality. Now we're going to have 3 equations instead of 3 inequalities with 3 slack variables, or we call it basic variables. Okay. So this box actually gives you the standard form of linear programming. In the standard form, we always maximize objective function subject to less than or equal inequalities. So this is very important. The standard form is maximizing something subject to constraints with less than or equal to. Now, if you have inequalities with bigger than or equal to, you multiply both sides by negative sign, you get less than or equal to. So it's always less than or equal to. Again, if you get bigger than or equal to, then you multiply both sides of this equation or this inequality by negative sign, you're going to flip the sign of inequality. So that's number 1 hint. Number 2 hint is, what if I want to minimize something? Well, let's say you want to minimize this function, all right? And you say, oh, this is not standard form, so I cannot do it. Well, actually you can. Well, if you are supposed to minimize this function, right? So let's say you want to minimize this function. If I multiply this function by negative signs, so I multiply through by negative signs, so I get negative c1 x1, negative c2 x2, all the way to negative cn xn. You want to maximize that one. So maximization of negative something will be equal to, or sorry, yeah, that's right. So maximizing negative of a function will be equal to minimizing that function. So minimization of something is equal to maximization of a negative of that. So this way you can convert all the problems to maximization with inequalities of less than or equal to. Okay, so this part actually is talking about the standard form and how we introduce the slack variables to convert inequalities to equalities. Okay, so let's jump into the example. So back to the example, we convert that linear program into a table, right? So the first one is the first inequality, just we derive the coefficients, x1, x2, and then 3 slack variables, s1, s2, s3. Equation 2 is right here, and equation 3 is like down there, and the right-hand side are all in the last column. This is the objective function, which we call it z, right? So you move all of them to the left side. This one actually doesn't have z in there. Well, it doesn't actually include the coefficient for z, but that's basically the same thing we covered in the notes. So anyways, if you just forget about the z, the coefficient for x1 is going to be -4 because it's gone to the left side. And this is also -6. Everything else is 0 because we do not have any slack variables in the first equation right here. Well, in the objective function. All right, so this is going to be my objective function. Now, there are 2 rules here. Okay, so we're going to follow the rules. Actually, before doing that, I'm going to talk about the optimality check. The optimality check is we look at the last line, and if we do not have any negative coefficients in the last line at the bottom of the table right here, this objective function, the solution to that table will be the optimal solution. So the check for the optimality is we should not have any negative coefficients on the last row below this table. The last row, I mean the objective function. Okay, let's start from the table. Okay, so the first rule was we have to pick a row. We have to pick a column corresponding to one of these variables, And we actually look at non-basic ones first. So non-basic ones are x1 and x2, and we pick up the most negative coefficients in the objective function. So out of these two, this one is the most negative, so we're going to pick this column. So this is called entering variable according to this book. The book calls it entering variable, and that's x2. Now within this column, I have to pivot a row. And to pivot a row, I have to pick up the smallest non-negative coefficient of right-hand side over the coefficients in this column. So we're going to do 3 calculations. 11 by 1 is 11. 27 by 1 is 27. And 90 by 5 is 18. Which one is the smallest? 11. So I'm going to go and pick up this row and make it a pivot. Okay? So the book calls it departing variable. So that's why we pivot this row. Okay? And then we're going to use arithmetic operations, means plus minus operations, by multiplying this row by some coefficient and adding or subtracting from other rows to make these two elements in the same column 0. So I want to make this one 0 and this one 0. And the book actually did that. So first, so by making these two 0, no, actually all of them 0. Now you see that the objective function is added to the table. And by doing row operations, this is before pivoting, and after pivoting you get this element, and this element to 0. You see that? Okay. And then we look at, so this is still, even if you go ahead and find the non-basic variables, you set the non-basic variables to 0 and you solve for the basic variables, you see that the solution is not going to be optimal because you still have a negative coefficient for the objective function. Okay, so now I'm going to look at the last row here and say which one is the most negative coefficient. That's this column. So I'm going to pick that column. Okay, so let's see. Yeah, this is still working on the first part. Well, actually, it's giving you the solution for this system, right? So we set the non-basic ones to 0. So this is non-basic, x1 equal to 0, and then x and s1 is also equal to 0, and then solve for, now you have 3 equations. We can solve for 3 unknowns, x2, s2, and s3. And turns out to be these, then you can go ahead and plug these into the last row here to get z, which is the objective function. Okay, it's minus 10 times x1, z, well, 0 times x2, and yeah, basically you get the 66. I mean, it's clear, even without doing any calculations, because we said x1 equal to 0 and s1 equal to 0, so these two are gone. The other ones have 0 coefficients, so z is going to be 66 anyways. All right, so the next step is to pick up this column and make it a pivot, or make one of the rows pivot. So I'm going to quickly jump into, so you see that and let me make sure that it picks up in the right column here. Yeah, and you see that here it says we're going to now choose x1 as entering variable because this row, the last row, has the most negative coefficient right here, minus 10. So we're going to pick up this column, and then within this column we look at the smallest non-negative ratio. So this is 35 by 7, right? So this is the smallest compared to 16 by 2, and this is negative, so we're not going to select that one. So this is going to be the departing row or the pivot row. So you see that if we keep this and then use this row to make other elements along this column, this, and that to 0. And you see this is what we get. And at the end of the day, we still have a negative coefficient in the last row. So that still need to be continued, right? So okay, so stay tuned for the next part on how we can basically finish this problem.